page 52. We're done. All right, so we've got this warm-up. It says find each angle measure. So think without speaking about what that would be. Whisper to each other. I said think without speaking. Gabby, or whispering. What would the measure of each angle be in number 1? 60 degrees. Y'all agree with that? Yes. Very good. Thank you, Gabby. All righty. And then now read number 2. Joshua, every equilateral triangle is isosceles. Is that true or false? It's true. So you were a little unsure, and then it's true, it's true. So tell me why it's true. So close. Lateral doesn't refer to angles. That refers to what? Sides. Okay. So is every equilateral triangle isosceles? No? Okay. Every equilateral triangle isosceles. So in an equilateral triangle, how many congruent sides are there? 3. What's your definition of an isosceles triangle? Okay, so is every equilateral triangle isosceles? Yes, because it says at least. Okay, good. All right. Number 3, Donovan. Every isosceles triangle is equilateral. True or false? False. You sure you kind of had a question mark on the end of that? False with confidence. Okay, good. All right, we agree with all that? Yes? Okay. So then, an isosceles triangle has, okay, Joshua, one more time. What goes in that blank? It has blank 2 congruent sides. What goes in the blank? Sorry. What is it, Joshua? At least. Sorry, couldn't help himself. Okay, at least. Now, if I'd have left out that blank and just said an isosceles triangle has 2 congruent sides, is that what you understood before we started talking about all this? Yes, but that word, those words "at least" in there are very, very important. Okay, so let's talk about the parts of the isosceles triangle. So here's a picture, and I drew it again where it looks kind of like it's laying down, right? There's not really a correct standing up and laying down. It could be whatever, but I know that's not normally how you see them, or have seen them in the past, and that's one of the reasons why I wanted to do it. But the congruent sides, so these 2 right here that are congruent, these are called the legs. All right. So these 2 things are the legs of the isosceles triangle. Now, a triangle has how many vertices? 3. So this is a vertex, this is a vertex, this is a vertex, right? But then there also is, for an isosceles triangle, the vertex. So this is a vertex, this is the vertex of the triangle itself. All right, so even though there's, yes, this is a vertex, but this is the vertex of the triangle. So right here it's created with the 2 legs. Since this is the vertex of the triangle, this angle right here is the vertex angle. Vertex angle. Okay, so all of the vertices have angles, but that's the vertex angle. That's meaning kind of like the top of the triangle, even though it's laying down. It's not really the top, but so the vertex angle is the angle formed by the legs. All right, so then the side opposite the vertex angle. So here's the vertex angle, the side opposite the vertex angle. Anybody know what that's called? The side, here's the vertex angle, the side opposite the vertex angle.
Oh, the base? The hypotenuse.
Okay, hang on. Let's pause. Back up to there. So he got all excited. Hypotenuse. And then he changed his mind, right? He said, nope, because it's for what? What'd you say?
I just said
Okay. What? But if hypotenuse only exists when? In a right triangle. And if this was a right triangle, that would be the hypotenuse. But they're not all right triangles. Okay, but then what did you say? The base. Okay. So this is the base of the triangle. Now, because it's laying down sideways like this, it's not sitting on the base, but that doesn't matter, all right? 2-dimensionally, 3-dimensionally, it does not have to be sitting on the base. That is super important for you to understand, especially when we get to the 3-dimensional stuff, because that will cause some of you to do something wrong pretty much every single time. Don't be that person or those people, because there will be multiple people. There always are every year. Okay? If I have a lamp, then the lamp is standing up like it's supposed to be. It's sitting on the base of the lamp, right? If I take the lamp and I lay it down, is the base still the base? Yeah, it's not sitting on the base anymore because it's laying that same kind of thing here. It's not sitting on the base, but that doesn't matter. The base isn't defined by what the triangle is sitting on. If I think about it sitting on a table, it's the side opposite the vertex angle. It's the side that's not the legs, basically. Okay, we good? All right, so the side opposite the vertex angle is called the base. And then the base angles are the two angles that have the base as a side. All right, yep, makes sense, right? So these are the base angles. Everybody okay with all that? Vocabulary is important? Yes, sir. Right. Now, let's say that it was just like a scalene triangle. Okay, so if it's a scalene triangle, you don't really have a base, you don't have legs. If you're a right triangle, but not an isosceles triangle, then it still does have legs, but it doesn't have a base. Does that make sense to you? Because the two sides of a right triangle that create the right angle, those are the legs also, whether it's isosceles or not. There's just a different kind of legs. Does that make sense? And then if it's an equilateral triangle, is it an isosceles triangle? Yes. So then you could pick any two to be the legs and any one to be the base. Basically, it just kind of applies to all of them. Okay, that's a good question. Anything else? All right. So then the vertex angle in this picture is angle 3, and then the base angles are 1 and 2. Okay. Everybody okay with all that? Yes. All right. Okay, so now we have theorems. Now, all the theorems and the corollaries we're going to talk about today, we've actually already talked about them. We just didn't talk about them as being an actual theorem. This is actually something that you knew before you came to me, but I know you didn't hear it as a theorem by that. But this says if two sides of a triangle are congruent, okay, so in this picture, two sides of the triangle are congruent, then the angle opposite those, and then blank. All right, so here are my two congruent sides. The angles opposite those are these right there. And what has to be true about them? They are congruent. So if two sides of a triangle are congruent, then the angles opposite those sides are congruent. So what type of angles are B and C? Yes, but what type of angles with reference to an isosceles triangle? The base angles. They would have to be acute because there's two of them, so it can't be obtuse, but they are the base angles. So angle B and angle C are base angles. And then by the theorem, because that means that they are congruent. So basically what this theorem is saying, without saying it in these exact words, is that the base angles of an isosceles triangle are congruent. That's not exactly what it says, because it does, in the isosceles triangle theorem doesn't even use the word isosceles triangle, right? It just says if two sides of a triangle are congruent. Well, if two sides of a triangle are congruent, that makes it an isosceles triangle, right? And then the sides opposite those, the angles opposite those sides are congruent. That means those are the base angles, and those are congruent too. So even though it doesn't use those words, that is exactly what it's saying. That's why it's called what it's called. We good? All right, so now the next one is a converse. So just real quick, because that's probably the first time that word's come up. That's part of what I skipped because of Harvey. That is not referring to the shoes, no. Remember, we talked about a conditional statement and how to write an if-then form. So if it looks like this, how do I read this right here? If P, then Q, right? That's how you read that. So the converse then, yes. It is if Q, then P. That means you can read it in both directions. A good definition of anything can be read as a conditional statement and a converse. That's why when I say parallel lines are two lines that never intersect, that is a true statement, right on. But if I read that as the converse, I would say if two lines never intersect, then they are parallel. Is that a true statement? No, it's not. Okay, because I also have the skew lines, right? So since I can't read it backwards and forwards, that's why it's not enough for the definition. That's why I have to say if two lines are parallel, then they are coplanar and never intersect. So then I can say if two lines are coplanar and never intersect, then they're parallel. And in both directions, it's true. That makes it a good definition, all right? Exactly. Yes, good way to look at it. Good job, good job. Okay. All right, so since this talks about we have congruent sides that gives us congruent angles, the converse is going to be we have congruent angles that gives us congruent sides. Okay, so just the opposite, just works backwards. So what this says, again, it doesn't use the word isosceles triangle at all, but it says if two angles of a triangle are congruent, then the sides opposite, so here are the angles, they're congruent, so the sides opposite them are congruent. So then I know that line segment ED is congruent to line segment DF. And what parts of the isosceles triangle are those sides? Legs. So line segment ED and line segment DF are the legs. So if we were thinking logically through a proof, can you look at this triangle and just know it's isosceles? And give me a reason why. Yes. The two sides congruent. So by definition, at least two sides are congruent, it's isosceles, right? So just by looking at this, can you tell me it's isosceles with one step? No. You would have to use this first. You would have to say, since the two angles are congruent, that means the two sides are congruent by the converse of the isosceles triangle theorem. And then since the two sides are congruent, that makes it an isosceles triangle. Does that make sense? So it would take you a couple of steps if we were having to actually write out all of our explanations. That's another reason why it doesn't use the words isosceles triangle in there. Okay, everybody good so far? All right. So let's look at this. It says find each measure angle, which makes no sense. This should say angle measure. Okay, what I meant. You know what I mean. Almost, but not really. Okay. I think what I was going for was find the measure of each angle, but that didn't really happen, and so whatever. But all right, let's look at A. So, what type of triangle do we have here? Isosceles. Okay, so these two sides are congruent. What does that tell you about these two angles? They're congruent. So if this is x, this is x, right? And so do I have enough information to solve for x? Yes. Can my first step be 2x plus 38? No. It is the triangle sum theorem, so it is exactly x plus 38 equals 180. So first step, zero work, you just plug it in. Then you can skip steps, and that's fine. So I can say 2x equals, I can go ahead and subtract that 38 over 142. So x equals 71. Does x equal 71 degrees? No. Am I done? No, because it didn't say solve for x. I have to find the measure of each angle. Well, they gave me that one. I don't need that one. But I have to say that the measure of angle B equals what? 71 degrees. Measure of angle C equals 71 degrees. Okay. Measure of each angle. There was two that I had to find. Okay. Everybody okay with that? Process. The more you can think algebraically and make things algebraically, the easier and quicker you're going to get through those PSAT and SAT problems. I promised you. Okay, I've already made you believers about some things. Maybe one day you'll finally realize I actually do know what I'm talking about. Okay, hopefully sooner than later. Now, what type of triangle is this? Isosceles. These two sides are congruent, which means these two angles are congruent. So do I have enough information to solve for x? Yes. So do I add them up, set them equal to 180? No. Equal. Okay. So x plus 30 equals 2x, right? Which means that x equals what? 30. I just subtracted x, and then I just moved it around. Yeah. All right. Am I done? No. So I've got to plug them back in. So I plug it into here, and for angle R, I can say 30 plus 30 equals 60 degrees, and that is the measure of angle R. So there's the first one. Then I can plug it into this one. 2 times 30 equals 60. That's the measure of angle S. Then, okay, so you recognize that, and that's good. But just because you recognize that now, that doesn't mean, you know, does equilateral or equiangular mean that just two of the angles are 60? No. So I still have to show my process. I still have to find angle T. So the measure of angle T plus 60 plus 60 equals what? 180. Which means then that the measure of angle T has to be 60. This is why it's 60 right here. Not because you have not because it's an equilateral triangle, because just having these two be the same does not give you the fact that it's an equilateral triangle. Does that make sense to you? So you kind of have to, that's really where it comes from, and then the NDS, because that's the only thing it can be. We're good? All right. So C says, a regular pentagon has 5 congruent sides and 5 108-degree angles. Use the figure and your knowledge of isosceles triangles to find the values of X, Y, and Z. Now, we haven't talked about pentagons yet. You probably have not used the words regular pentagon at all, or even know what that means, but it doesn't matter because it told you everything you need, right? So sometimes you're asked to do things you haven't done yet, but it doesn't matter because they give you so much information. And it actually says, use your knowledge of isosceles triangles. It's like giving you tons of information. It even tells you what direction to go. It doesn't just say, hey, find X, Y, and Z. So do I have enough information right now to find the measure of angle X, or to find X? Yes, because it even tells me, use your knowledge of isosceles triangles, right? So this right here is an isosceles triangle. So if this is X, what's this? X. So I can say then that I know that X plus 108 equals 180. Okay. So 2x equals what? 72. So x equals 36. All right, so this is 36, and this is 36. Now, the skinny triangle in the middle, is that isosceles? Can't prove it right now yet? Okay, so let's think about whether or not we really have enough information in it. Do we feel like it probably is? Okay, so let's see if we can get some actual proof in there somehow. It tells me that all the big angles are 108, right? So what's this one? 108. So what does this have to be? No. This has to be 36, and so does this, because that's what happened over there, right? Okay, so if this whole angle right here, what's the measure of this whole angle? 108, right? All the big angles are 108, right? That whole thing. So isn't this whole thing 108? So since these two big ones are the same, and they each have a piece of 36 being part of it, then do these two angles right here have to be the same? Yes. So this angle and this angle is the same, which means this is y. So then is the skinny triangle isosceles? Yes, by the converse of the isosceles triangle theorem, right? These two angles are congruent, therefore these two sides are congruent. You see how that works? All right, so now, do you have enough information to find y? Yes. How?
Because you know that the whole thing is 108.
Good. So x plus y has to give me 108, right?
Yeah.
And I know x, so by the angle addition postulate, 36 plus y has to equal 108. It doesn't have anything to do with triangles at all. Okay, does that make sense? Good? All right. So then y equals, so 108 minus 6 is 102, then minus 30 you get 72. Is it degrees? No. So 72 and 72, can you find z now? Yes. So z is part of this isosceles triangle in here, so z plus 72 equals 180. So what's 72 plus 72? 144. So z equals? Okay, so what's 3 times 36? Just tell me. You should be able to tell me like that right now. 108, right? Because look at this. 36, 36, 36. So 3 times 36 is 108. Right? Didn't have to do any math because I could just see how it works up there, right? All right. Any questions? We good? Yes, ma'am. Yes, because it tells me right here that the 5 angles are 108. So this is 108, this one right here. And so is this one. So this whole thing is 108. And this whole thing is 108. That's how I know 3 times 30. And this whole thing is 108. Because it's the big angle of the pentagon. Does that make sense? Okay, good question. Anything else? Yes? Good? Awesome. Okay, so the next thing is a corollary. Remember, a corollary is just a theorem that comes from a theorem. And we're actually going to use the isosceles triangle theorem, even though we already know what the answer to this is, probably, right? If a triangle is equilateral, then it has to be what? What kind of equiangular? Okay, not obtuse. Cannot be obtuse. Obtuse would be a no, but equiangular, yes. And remember, it is not equal angular. There's no L right there. Equiangular. It's much easier to say that way if you don't try and stick that L in there. This is true because of the isosceles triangle theorem. The isosceles triangle theorem says if two sides are congruent, so we'll start with these two. If these two sides are congruent, then the angles opposite them are congruent, right? So that makes these two congruent. Make sense? Then I'm going to apply the isosceles triangle theorem again, and this time I'm going to use these two sides, and the angles across from them are congruent. Since this one's already marked with 1, this gets marked with 1 also, and that makes all 3 angles congruent. So it's basically just using the isosceles triangle theorem twice. That's why that happens every time. Okay? Okay, look. These two sides, listen, these two sides are congruent, so the angles across from them are congruent, right? B and C. Then I'm going to also look at, well, these two sides are congruent also, so the angles across from them, A and B, are also congruent. So if B is congruent to C then and B is congruent to A, then all 3 of them have to be the same. So it's basically just using that theorem twice, okay? And which you don't have to do anymore because we have this corollary. So what we know here then is that angle A is congruent to angle B, which is congruent to angle C. And the measure of angle A is equal to the measure of angle B, which is equal to the measure of angle C, which is equal to what? Not 180, 60. So I'm setting them equal, not adding them up. Everybody okay with that? And that's why also, if you do the converse twice, that's why if it's equiangular, it has to be equilateral. Like it goes in, again, in both directions. We all good with all that? All right. So I know the way that most of y'all look at problems is like you don't even really read the directions. You just like look at it and you see something and you just randomly start doing stuff. You need to back it up a little bit. It doesn't take an extra 30 minutes per problem. I'm like 2 seconds per problem maybe. And you need to start analyzing what you have. Like what they gave me, and I know it says it too, but it doesn't need to say it. It says the triangle is equilateral. And it's labeled, so both of those things didn't have to happen, one or the other. But it's given you that it's equilateral. But then it's asking you for something with angles, right? You know it's equilateral, and then that means the triangle also has to be what? Equiangular. So that means that all 3 of these are congruent, right? So if this is 3x plus 15, so is this, and so is this. So can I add that up 3 times and set it equal to 180? Yes. Could I do it easier than that? What could I do, Sandal? Just set it equal to 60, right? I could add it up 3 times and set it equal to 180. Nothing wrong with it. It's correct. Sometimes you're not going to recognize the easier way right away, and that's okay. Don't spend time trying to find the easiest way because there may not be more than one way. But yes, we also know that they're all 60, right? Because it's equiangular, so I don't have to do that. I can just say 3x plus 15 equals 60. So 3x equals what? 45. And x equals 15. Am I done?
Yes.
Yes. If I plug it back in, what am I going to get? 60, because that's where it came from, right? And sometimes what happens on problems like this, you plug it back in, you get 60, then you're confused and you think you did something wrong because that says 60, and then you spend way more time than you need on a problem, whereas if you'd have just gone back and reread what you were looking for, you were done a long time ago, okay? And you're the reason you're confused because you just keep on doing stuff, right? Okay? A lot of times, yes, a lot of times you're the reason you're confused, not going to lie. All right. Now this says, again, it says it's equiangular. It doesn't have to tell you that, but if it's equiangular, it also has to be what? Equilateral. So can I set this equal to 60 and solve? No, because it's a side length, right? All right, you work on that one while I hand out the homework. Okay, good. If you, he just said I already confused myself, but then I regained it. When you, that's going to happen sometimes, right? You overthink something, your mind gets all mixed up. Just stop and start back over, reread it, and pretend like you're starting from the beginning, right? So I can set them equal to each other, even though I don't have that one. And that means that 9 equals 2t. So what does t equal? 9 over 2. Is 4.5 okay? No. Is 4.5 okay? No. Do both of those require an extra step? Yes. So just learn to stop, right? You are done.